So this last little stage of kinematics, what we're looking at is projectile motion. And so the key you've pretty much learned everything you need to know to do projectile motion. There's just one concept to get across, and that's this idea that when you've got a projectile, so it's something that's fired, it's got initial velocity, and then after that, the only force that's acting on it is gravity. And so what you can do for projectiles is you can separate the horizontal and the vertical motion. And so to get an idea of what the horizontal motion would be, so for example, with this example here where you've got a cannon firing a cannonball, for that horizontal motion, to figure out what that would be is just ignore the fact that there's gravity there. So we just ignore gravity and we just think about what would its horizontal motion be. And we're assuming that air resistance is negligible. Therefore, there's no force. If there was no gravity, there would be no force acting on this particle in the horizontal direction, or this cannonball in the horizontal direction. Therefore, it would have constant velocity. So you only get acceleration if there's an unbalanced force acting on the object. And so it would be moving at constant velocity. And so you just find that the particle would move at equal distance for each time interval. In the vertical direction, you've got acceleration acting on that particle. So we'll use those equations of motion for acceleration. And you can just think about where that particle would be vertically if you just dropped it, or maybe you throw it up a bit. Throw it upwards, but you're just thinking about, without a horizontal component, what would that particle do? And you can figure out where that particle would be after a given time. So in this one, it's got no vertical velocity to start with. The example we'll do, it does have vertical velocity to start with. We'll get to that in a minute. And so what you do is you figure out the motion horizontally, which is just constant velocity. Then you figure out the motion vertically, which has got constant acceleration. So it's the equations of motion for each of those: constant velocity, constant acceleration. And when you put those together, you get the position of the particle in the x and y directions. So you just use the same time to calculate horizontal distance and vertical distance. You'll get the vertical displacement, the horizontal displacement, and that'll tell you the xy coordinates of this little cannonball. And so you can just plot those and you can figure out the parabolic curve, so the path of this cannonball, just by drawing a smooth curve through those. This little image here is just showing the same thing. So they've done it experimentally. They've had one ball that they've dropped vertically. They have another ball that they put a small horizontal component of velocity before it was dropped. So it's maybe rolled along here and then fallen out. And what it's showing is that for a given time, so each of these lines is at a given time, the ball that's got a horizontal component, its vertical position is no different from one that's dropped horizontally. And similarly, what we were just talking about before, if air resistance is negligible, then the distance it travels in the horizontal direction is constant between each time interval because it's moving with constant velocity, no forces acting on it. Okay, so those two examples are when you've just dropped a ball. What we're looking at in this example here is a case where what we do is, well, let's just have a think about it. This is just being, initially, it's just being fired horizontally, but you don't have to do that. You could fire it upwards, you could fire it downwards actually as well. And so we're just extending this idea to a slightly more general example. So the first step in this, let me just think how I'm ordering all my, so what I've done is just drawn a bit of a sketch. The first step is you look at that velocity and you separate it out into its horizontal initial, so this is an initial velocity. You separate it out into its horizontal and vertical components, and that's just using normal trig. So what we're going to do is what do we have to do actually? What's it asked us for? So it wants the equations of motion first. So we're just thinking the equations of motion are the acceleration at time t is just going to be constant, or it might be zero. This is for, well, let's just do them both. So this is for constant acceleration. These are equations of motion. Again, these are something you have to learn. I think I'm misspelling this all the time. Acceleration. And we'll also write down for constant velocity. So the equation of motion would be for constant acceleration. The acceleration at time t is just a naught, it's constant. Then we've got the velocity at time t. Let's just check we're zoomed in here. Nope. So the velocity at time t is going to be equal to initial velocity plus acceleration times time. and the displacement at time t is going to be equal to the initial displacement plus the velocity times time plus a half times acceleration times time squared. So those are going to be the ones we're going to use. So these equations are going to be the ones we're going to use for the vertical direction, because it's got the gravity acting on it. For constant velocity, we'd have the acceleration at any time is just 0. Then we'd have the velocity at time t is just equal to v naught. And it comes from this equation. You only need to remember these equations, then you just remember that this is 0, so vt is v naught. And then displacement at time t is just equal to s naught plus v naught t. What we will do, though, is when we're putting them in for this kind of parabolic situation, we'll just make sure we're clear about what's x and y. So we'll probably call this a. Well, this would be a naught x, this would be v naught. Oh, sorry, this is in the y direction. It's the constant acceleration. So this would be a naught y, v naught y plus a naught y t. And we'll probably just call this displacement, we'll just change that to y. Okay, it's just the y. So the y coordinate's the same as the displacement in the y direction from the origin. And these ones would be x, ax, vx, and we just change this to x. And then we'd have v naught x, s naught x, v naught x, so on. So let's work through that. The first things we need to sort out is what are these components. So we need to separate this velocity vector into its x and y components. And we'll probably do, let's do the x first, constant velocity and all that. So we are going to have, let's write out what we're doing, equations of motion in x. So we'll just do equations of motion. And let's say x direction. And then over here we'll have the y direction. Let me just bring the ruler here. Motion. So in the x direction, we have acceleration is 0, so don't even need to worry about that, but we're going to have v naught is equal to, so the v naught's this horizontal one, so it's going to be 180 cos 30, 180 cos 30, which is equal to, let's find my calculator, it's equal to 155.9 meters per second. That's cool. S naught, so in the horizontal direction, we'll just, oh sorry, haven't written the equation of motion yet, and so it's constant velocity, so v in the x direction at time t is just going to be equal to v naught, call that equation 1. Then we're going to think about the displacement, and so in the x direction, we'll just choose the start point as 0, so therefore our s naught is going to be 0. So therefore we're going to have x component, so instead of writing displacement, we'll just write x. X of t, it would usually be s naught plus v naught of x. Well, let's just make sure we put that, v naught x. So it would usually be, just go back up here again, it's this one here, be s naught plus v naught t. In our case, we're in the x direction, and that initial displacement we're just going to take as 0, therefore it's just going to be v naught x times time, call that equation 2. In the y direction, so we have acceleration in the y direction at time t is just going to be minus 9.81 meters per second. Now we're taking minus because we're going to use up positive, so we've got y shown here and it's positive upwards, so we'll take it as minus 9.81. Then we need to know our v naught, so they'll call this we probably don't even need to give that a name because we probably won't use it again, but let's just do it anyway, so we'll call that equation 3. Then we are going to have, so v naught in the y direction, so this is just the initial velocity, is going to be 180 sine 30 degrees, which is going to be 90 meters per second. because sine 30 is just a half. Therefore, the velocity in the y direction at time t is just going to be equal to, well, it's going to be v naught y, so it's going to be 90 plus at, but it's a negative acceleration, so it's going to be minus 9.81 t. Call that equation 4. And then, what else are we left with? So we want to find y. Now, so y naught, we could choose y naught as 0, and then this would be minus 150, but let's just take y naught as 150, so it's starting 150 above ground level. We'll take ground level as 0, so therefore we're going to have, we'll just write this out, y naught is equal to 150 meters. Therefore, y naught at time t is just going to be equal to, we maybe should write it out, y naught plus v naught y times time plus ay time, or a naught y, whatever you want to call it. It's just a constant. It's the initial acceleration, but it's actually the acceleration at any time because the acceleration is constant, and it's a half a naught y t squared. So y naught, so that's 150. The initial velocity is positive, y direction, so the initial velocity is going upwards. That's it here. That's moved nose to tail, so I've drawn it dashed. So it's going upwards, so that's positive. So it's going to be plus 90t minus a half times 9.81, so it's in the negative direction, so it's minus, so that's 4.905 t squared. Call that equation 5. And we're not going to write down the velocity ones. For the problems we need to do initially, maybe we should just write it out, because the ones that I haven't written down yet, I'm just trying to think whether I'm going to need them or not, is the v at position. So v squared s is equal to, so let's have a think about that for a second. Position in 4 seconds. Find that time. I'm just trying to think greatest elevation. Horizontal distance with a projectile. So I am not sure that we're ever going to need the fourth formula in this question, but for completeness, let's just write it out. So that equation is v squared at position s is equal to v naught squared plus 2a s minus the initial position, initial displacement. And if we wanted that for here, well, our displacement is just the y, so we'd have v squared y is equal to v naught squared, which we know we do. It would be equal to 90 squared, and it's negative acceleration, negative 2 times 9.81 times y minus y naught. So that's going to be equal to 90 squared, must be 81,000 or something. Yep. Sorry, 8,100. 8,100 minus 19.62 times y minus 150. And then we've got all our equations 6, whether we need them or not. So if you're in an exam, maybe you don't need to write them all out, you just need to figure out which ones you need. So what's next? So we've got the equations of motions. Now it wants to know the position of the projectile at 4 second intervals during the flight. So we're just going to draw a couple of diagrams here. What's going to happen is I've got a couple of little sketches here to start with. And so we're going to get this little particle in the vertical direction. So really it's heading off this way, but in the vertical direction only, what's going to happen is it's as if you'd just thrown it directly upwards. It'll start reasonably fast, it'll go up, it'll slow down, and then it'll speed up towards the ground, and then it'll hit the ground there. That's what's going to happen with that one. With this one, with a horizontal component of that motion, it's just going to be traveling along at constant speed in the horizontal direction, like so. And then when we put those two together, we will get a graph of this. So let's just do the graph, I think. So at 4-second intervals, I might even update the question to say that's what we're doing. So easiest way just to do that is just to create, let's just create a bit of a table. So we're going to have time, and then we're going to have the displacement in the x direction, which is just the same as the x coordinate, and the displacement in the y direction, which is the y coordinate, and it wants us to do it at 4-second intervals. So we'll start with 0. Might need a bit more space than that. 4. Have we figured out how many seconds it's going to take for it to hit the ground? Not really. It would probably be easier if we figured that out first for the duration of the flight. So let's just figure out how long it's going to take for this projectile to hit the ground. So when we're doing that, what's important is the vertical position. So it's going to hit the ground when the vertical position is equal to 0. If it wasn't for us, so the horizontal, it's just going constantly in the horizontal direction. If there's no gravity, it would just keep going on forever. But there's gravity, and that's what's going to make it hit the ground. It's when this vertical component gets to 0. So just before I do this here, let's just figure out the total time of flight. So for time hits the ground, well, at that point, the vertical displacement, the y displacement, is going to be equal to 0. So we're going to have y naught of t is going to be equal to 0, and that is going to be equal to, this is equation 5, and that is going to be equal to 150 plus 90t minus 4.905 t squared. So we've got ourselves a quadratic equation. So let's get it in the right order. I'm just going to take everything to the other side, and so it's called the first things, everything's going to change sign. Just going to add it to both sides. I'm not just swapping sides, I'm taking it to the opposite side. So 4.905 t squared minus 90t minus 150 is equal to 0. So let me just go through and solve this. So we're just using the usual formula. Let me just work through and solve this, and then I'll come back. So I've worked through that. I've got it in the form something, a number times something squared, plus or minus a number times something, plus or minus a number. So you get your t squared, your t, and your number. So from that I can get my a, b, and c. Stick that into square root b squared minus 4ac. You get that value, and then to find the value of t for which this is true, you're just sticking it into this equation, negative b plus or minus the square root b squared minus 4ac. That's what we calculate here over 2a, and we've got our answer there. Now you'll notice one of these answers, 90 minus 105, you're going to end up with a negative time, which has no meaning in our context. And so we're talking about before, so if you went backwards in time, none of these equations would be valid. It wasn't moving with this acceleration before that time. So that's the time at which the y component is going to be 0. So that's the time where this hits the ground. So it's 19, so it's about 20 seconds. So we'll do 4-second intervals. I think it asked for 12, 16, and we would go to 20, but that would be beyond the end of the motion. So we'll just do 19.88 for our last one. So then we're going to figure out x's and y's. So let's get those x's first. And so our equation for x is just the velocity times time, and the velocity component in the x direction was, I should have written that in really. So let's just do that now. So that is equal to 155.9 times time. So we're just going to use this equation to figure out the x values. So it's going to be 155.9 times 4 for the first one. So initially it's 0. We're taking 0 coordinate for x as our starting point. Next one would be 623.6. Now it would be 1247. It's quite a long way, but it is a projectile after all. And then I'll work out the rest of those as well. So all I'm doing is taking that equation to figure out x, putting these values into it for the different times, So I'll just do that. Then do this. Then we'll do the same thing for the y component. And so we've got the equation for the y position at time t. Finding all my mistakes as I go through this. Not why not, it's y at time t. So the y coordinate at time t is given by this equation 5. And so just copy this down probably. And I might do the same for the x coordinate in just a moment. I'll just put that in grey just so we know where these are coming from. So what I'll do is just plug the time into this equation. So for the first one, it's just going to be 150 before it starts moving. That's the initial position because the t's are equal to 0. And then I'll just substitute 4 into here, get the answer, substitute 8 into here, get the answer. So just work through it and find those y positions. So that's those. So figure out x coordinates at those times, y coordinates at those times. We should really put in units here. So time in seconds, displacement meters, height in meters. So then if we wanted to know the actual path of this, what we do is just plot these in a graph. And so I'll do that as well. And then come back again. Okay, so I've drawn up some axes. I'm just thinking about what I'm going to do next. So still haven't really finished them. So this is y, also in meters. So let's just start plotting some of these points. And so this is the x coordinate, y coordinate. So we're starting 0 displacement. So this is at 0 seconds. It's going to have x coordinate 0, y coordinates 150. Then we're going to have x coordinate 620-ish. So it's around, so this is 750, 6 might be there. So it might be about here. Should plot it more accurately. So we put 623 and y is going to be 413. So about here somewhere. Then we have got at 8 seconds, it's going to be 1200, which is around there, 1247. And the y is 556. So 550 would be here, about here. At 12 seconds, we're going to have 1870, so that'd be 1750, 18 might be here, 19 about there, so 1870, so about here somewhere, 523 is going to be around there, 2000, pretty much 2500 is at 16 seconds, and it's 334 about here, and then at 3100, so that would be 250, 2 might be about here, 1 might be there, 118 might be about here, it's going to get back to 0. And so to plot the flight of that, bearing in mind that the scale is not the same on both axes, so it looks something like that. Trying to plot as smooth a curve as I can. Always looking forward to the next point. Don't like that much. A bit ugly. Try that again. It's easier to do on a piece of paper than it is to do on a screen. Okay, so the flight will look something like that. So you've got this parabolic shape. It should actually be symmetrical, but it's probably not far away. Okay, so that was that. So that's just showing how this works. So if you're trying to figure out how this projectile motion goes, what you're basically saying is you're figuring out equations for the x direction and the y direction, and those two things are independent. So basically you can think about the height as if it had no horizontal direction. It's going to be the height of that little object, and the x position is going to be as if there was no gravity. That's where the x position would be, just heading along horizontally, as if you just fired it horizontally with no gravity. It's just been constant velocity. And if you want to know the position, what you do is you just figure out the x and y positions at different times, plot them together, and then you'll get a a graph of the path of that projectile. Let's try and solve some of the other problems it's asked us to do. So find the horizontal distance from the gun to the point at which the projectile hits the ground. So in this case, so what were we up to here? This was part A, was it? So this was part A. This here was part B, where we figured out the positions. And now we're on to part C. And we've already calculated that actually for part C. Horizontal distance from the ground to the point at which the projectile hits the ground. And so it's looking for this distance, which is just the x coordinate when it hits the ground. And so we'd already figured that out just to figure out how big to make this graph. So let's just do it over here so that we can see it's an answer. So horizontal distance to point at and it was, what was it, 3,118. So 3120 to 3 significant figures. Now we could do a quick check on that. So, or could we? Maybe that's the only way to do it. Horizontal distance to the point at which it hits the ground. I'm just trying to think if there's another way we could have got that. Not really. Not really. Just leave it as that, I think. So part D, because I was thinking, is there some way I could use this equation here to figure that out? This v squared one, but there isn't really any way to do that because we're not really taught, we don't know the vertical velocity of the projectile when it hits the ground. It's not like finding the maximum. But I think that's the next question, isn't it? Determine the horizontal, find the greatest elevation reached by the projectile. So that one is where we're putting v equals 0. So at, let's say, max height. At max height, the velocity in the y direction, equals 0. So then we just need to think which equation are we going to use. Now we could use this one, which is probably going to be the quickest way to do it because we know that this is going to be 0. The velocity at this position is going to be 0, and it's going to directly give us the y coordinate or the y displacement for that. And so that would work well. I could do it another way. We could also figure out the time. Let's just think. We could use this equation because that we know that that velocity is going to be 0. That would give us the time at which it was at the maximum height. And then we could substitute that into the equation for the height. We could substitute that in here, and that would give us the height, so 2 steps instead of 1. But just let's use equation 6. So because it's so far away, let me grab it. Let's write it out in full so I can grab it down. So vy squared is equal to all of this. Save me. And so we could also say it's the same thing. Vy at position y is also 0. So therefore we have from 6, so it's from equation 6. We'll just write it out first. So v squared y, is equal to 1,800 minus 19.62 times y minus 150. And at the point at maximum height, that's equal to 0, is equal to 8,100 minus 19.62 times y minus 150. So y minus 150 is equal to 8,100 divided by 19.62, and then we could figure out y. We could just write that now. 100 divided by 19.62 plus 150, which is equal to 8,100 divided by 19.62 equals plus 150. It's 562 meters. So I could do a check on that, doing it the other way. So use equation 4 to find out what time it had zero velocity. Substitute that time into the y displacement at time t. But we've already drawn this graph, and we know that that must be about right. So we've got 566. It's not going to go much higher than that. And so this answer of 562 seems reasonable. So it seems reasonable that that's the right answer, so probably don't need to do a check on that. So max height equals 562 meters. Don't forget to underline your final answers. And it's above the lower ground level, because we took the lower ground level as our datum, but let's just check. We just need to double check that that's actually what the question asked for, not the height above the cliff or something like that. It's just saying the greatest elevation reached by the projectile. So I would have said that's the elevation of the projectile, is above the lower ground level. Determine the horizontal distances, this should probably be distances, at which the projectile has a height of 180 meters. Fair enough. So we can guesstimate that from this. So it's going to be very close to the start. You see what I mean? The point at which is 180 meters high is around here somewhere. So there's going to be 1 point here, 1 point here, something like that. And so it should be 2 points at which that's the case. So let's figure that out. What are we going to use to do that? What was it asking for? Time? Horizontal distance at which that's the case. So let's think about how we're going to do that. So we want the horizontal distance at which the projectile has a height of 180 meters. So what we're going to have to do first is we're going to have to find the time at which it's at 180 meters using the vertical equations of motion. Then we're going to have to use those times to find the horizontal distance at those times. So we'll substitute that time into here to find the horizontal distance at which that is the case. So this is now part E. For height 180 meters. We're going to use, so what we're going to know there is that y of t is going to be equal to 180. So we're going to use another equation. So let's have a look at which equation we're using. This one, hold on, y, so y of t, so it's this equation 5 here. So let's grab that, bring it down just so I can see it. Just make that one grey as well, just for thinking. So let's just get rid of the from, we'll just say 5. And that equation is y of t is equal to, so write out the equation first, 150 plus 90t take away 4.905t squared. So therefore we're going to get, we want to know when it's, that height is at 180 meters, so that vertical displacement is the same as the height in our case, plus 150 plus 90t minus 4.905t squared. Now, to solve this, we need to get in the form of a t squared, then a t, then a number, not two numbers or anything like that. So we're going to get, I'll just bring all this to the other side. So it's going to be 4.905t squared, adding it to both sides, minus 90t, and then it's going to be 180 minus 150, which is going to be plus 30 is equal to 0. And then we just go ahead and solve that in the normal way to solve this type of equation. So let me just pause it here and I'll try and solve that. So substituted, or what have I done? So I've rearranged it, so I've got it in the form that I need. And then I figured out a, b, and c, and then b squared minus 4ac. Figure that out first. And then to get the time t, you're just using the standard formula, minus b plus or minus b squared minus 4ac over 2a. And in this case, both of those answers, it's plus or minus, both of those answers are valid in this case. So you've got one at 18.01 seconds. Let's just go back up here and see. So this was, so the total time at the end was about 19 point something. So 19.88. So this answer of 18 seconds for this point seems quite reasonable. And similarly, the very short time at this end. So this point here was at 4 seconds. And so this 0.81 does seem reasonable as well. Sorry, 0.339 for that first point seems reasonable. So we've got the two times at which it was at 180, but it wanted the horizontal distance. So now we're going to just substitute those values. What I might do, because we've got these two values here, I'll just call this T1 and T2. So to get for horizontal distance, sub T1 and T2 in. So we want the equation for the horizontal distance at time t, which was equation 2, which is this one. Let's just drag that down. So we set that in 2. So we are going to get x1 is equal to 155.9 times t1, which is equal to 0.01 is 2808 meters, and x2 is equal to 155.9 times t2, which is equal to 155.9 times 0.3394, which is equal to 0.3394, equal to 52.9 meters. Then just write out our answer. The projectile is at a height of 180 meters for horizontal displacements of 52.9 meters and 2808 meters. I think we're finally done. Okay, so it took us a while. Key points when you're analysing these projectiles, the first thing you're doing is it'll tell you your initial velocities. If it's horizontal, v0y is just 0. If it's straight up, v0x is just 0. But otherwise, you'll determine each component using sine, cos, and tan. And that way, you can get your initial velocity. For projectiles, the acceleration in the y direction is always minus 9.81. It's just gravity acting in the y direction. In the horizontal direction, usually, well, in this course, always, you'll be assuming that drag is negligible. Therefore, you can assume constant velocity in the x direction. And so you just think of those two things separately. You can get all your different equations of motion for each of those directions. And then from them, depending on what the question's asking for, you just pick the right equation and get your answer. So the way it's working is really what we're doing is we've got two different equations. One of the equations is going to give us the x component, one is going to give us the y component. If you plot them both together, you get the actual motion of this projectile. Then, yeah, like I say, so you're just selecting the formula you need to solve the problem. Sometimes you're going to have to do it in 2 steps. So if it's asking you for the horizontal distance at a certain height, well, you're going to have to use the vertical equations of motion to find the times at which it's at that height, and then take that height and substitute it into the horizontal equations of motion, and you'll get